Well, good afternoon. This is Monday, the 24th of September, 2018, 12:21. We're actually 6 minutes late getting started. It's supposed to be Cal 3 class. Right now, I'm the only one in the room. Don't know where everybody is, but hopefully they'll be showing up soon. So let's get started from our current slide. We finished 12.3 last time. Did not get quite have a chance to get started on 12.4, so let's hit 12.4. Chapter 12, of course, is vector-valued functions, and 12.4 is tangent vectors and normal vectors. Sorry, my throat's been like this all morning. I don't know what the problem is, or not all morning. It's my last class and this class. First of the morning, it was fine. It says find the unit vector. The objectives here are to find the unit tangent vector and a principal unit normal vector at a point on a space curve. Okay? Couple of sort of new terms here. I think we talked a little bit about a tangent vector. I don't know if we got it down to a unit tangent vector. I don't remember. But the principal unit normal vector, I think, is sort of a new concept here, but not completely, as I think you'll find out. And then we'll find the tangential and normal components of acceleration once we have that. Okay, so let's start with tangent vectors and normal vectors. The velocity vector points in the direction of motion. Okay, if you got a curve, something's going in space along a curve, the velocity vector points in the direction of the motion. That observation leads to the next definition, which applies to any smooth curve, not just to those who are for which a parameter represents time. Okay, which of course it would be if that was a velocity vector. So the definition of a unit tangent vector is this. Let C be any smooth curve. Sorry. Man, this is terrible. Represented by R, that's your displacement vector. Okay, now that's in sort of physics terms, but whatever your independent variable is, the R is the vector that represents from the origin to some point on that curve C. Okay, on an open interval I, where I would be the parameters of your independent variable. It doesn't have to be time. It is if you're dealing with displacement and velocities and accelerations, but it could be any independent variable t, which doesn't have to be time, or any other variable, s, or whatever you want it to be. Okay? The unit tangent vector, capital T of t, is then defined as the first derivative of that displacement vector, that's just to give it a name, I can't think of anything else to call it, the R vector, first derivative of the R vector with respect to t, divided by the magnitude of the R vector, because the first derivative of the R vector with respect to your independent variable, that will be your tangent vector. Tangent vector, no matter what's going on here, whether R is displacement and t is time or whatever they happen to be, but that's going to be a tangent vector. Divide that by the magnitude of that tangent vector, and you're going to have a unit tangent vector. I mean, it's in the direction of the tangent vector with magnitude 1. That makes it a unit tangent vector. And that's capital T of little t, t. Okay. Now, of course, the displacement vector or your R vector, the first derivative of that cannot be 0, or else that doesn't make any sense. Okay? So in other words, basically, in terms of the physics type definitions, your speed can't be 0. In other words, it can't be at rest. If it is, it's not going anywhere, so it doesn't have a unit tangent vector. So with these other things, same type deal. If there's no change in your R vector with respect to time, then it can't have a tangent vector. So obviously, that R vector cannot be the 0 vector. The first derivative of the R vector cannot be the 0 vector. We know that a curve is smooth on an interval when r prime is continuous and non-zero on that interval. So smoothness is sufficient to guarantee that a curve has a unique tangent vector. Okay, r prime is continuous and non-zero. Okay, all right. So here we go. Goodness gracious, why is my pen over there? All right. Example 1. Find the unit tangent vector to the curve given by this equation, vector equation. R of t is equal to ti plus t squared j. So this, all indication, this is only in 2 space, no 3 space component here. Well, when t is equal to 1. Okay, so the first thing we've got to do, of course, I wish some of y'all were here, is take the derivative. So r prime of t would be what? If you were here, I hope you'd say I plus 2t j. Okay? Now, goodness gracious, I'm about to sneeze. For some reason, it's just gotten... extraordinarily cold in here. I don't know why. And I just had my head all clogged up. Sorry about that. Now, I'm trying to think if there's any special order that you need to do with this. Yeah, I think you've got to do your magnitude of r prime next. Magnitude of r prime of t. Don't plug in the 1 yet, okay? And this is going to be the square root of 1 plus 4. No, I'm sorry. 1 plus 4 t squared. All right. I'm so glad you're here. I get so sick of talking to myself. So, yeah. Would you pronounce again for your name for me?
Christina.
Huh?
Christina.
Christiana?
Christina.
Christina.
Yes.
Oh, okay. I'm sorry. It does have, yeah, an extra I at the end. Yeah. Or I at the end. Right, I see. Christina. Okay. My hearing's not good, and I was trying to figure out how to get all those syllables in there. Okay. All right. Here you go. And did I tell you before, I did go down to both we went to the registrar's office together, didn't we?
Right.
And saw that you were done. Later, I went to the cashier's window to make sure they said, yep, all paid and everything. So I don't know why the asterisk was by your name or why you weren't sure on the roll. But I do believe, if I'm remembering right now, it happened in at least one class. I think it was this one, but I believe it happened in 2 or 3 of my classes. They had taken people out of the class and then put them back in. And it's just because they had made a mistake. And the system was just all screwed up. The gal down there in the records office is saying, the system is just really lousy. It's just, and we've got calls in all over the place on them. And so I don't know what was going on, but it hopefully is taken care of now. If I'm not mistaken, you're back in, and everything is as it should be, except, if my memory's right, there was still an asterisk by your name. And I don't know when they're going to get that taken out, but you're in there. All right. Oh, man. I usually don't turn on the projector, no students are in here to read it. And I usually don't turn on the light unless computers are in. unless it's dark outside. It's light outside. And shortly before you came in, I just had a sneezing fit I couldn't control, and now my head's all clogged up. So I might need to run up the hall just to clear out, but I'm going to try not to now. We're doing example 1 on page 845. I meant to, when I turn on the turn on the Screencast-O-Matic to go over these few announcements again. I think I've announced them last time. Did I ask about fall graduation? Yes. And spring graduate? Are you graduating either fall or spring? No. Okay. And if you know of anyone, this is a great time. Well, for fall, you got to have your application in now, but for spring, this is a good time to get started on it. And there's 3 steps of the process: degree audit, your advisor, and then applying online. But share the word, and then remember, the term before you graduate, that's the time to apply. Okay? That way you get everything lined up in advance. Okay, and also the Office of Student Services is looking for seeking students who are interested in becoming note takers. They obviously have some students who can't take notes because of some physical disability, so they will pay you to take notes. And also the Space Center, I'm so sorry. Space Center is looking to hire, paying you money, peer tutors in the areas of math, English, biology, computer science, and Spanish. You are a prime candidate for math, and probably some of the others too. So please give that a look too. I've got the information here if you want it. Okay. We were doing example 1 on page 845. Sorry, my head is so clogged up I can't talk well. It says find the unit tangent vector to the curve given by this. It's a plane curve. R of t is equal to ti plus t squared j. Now, this does not have to be a displacement vector. We're used to seeing that in physics as a displacement vector. It can be any kind of vector. T doesn't have to represent time. It could represent anything. And how r is changing with t, and we want the tangent vector, unit tangent vector. Well, no matter whether you're talking about time or whatever, the tangent to that curve is its first derivative with respect to the independent variable. So that's why the first thing I did was take the derivative of that, and that was I plus 2tj. Okay. That is a tangent vector to that curve. It's got to be. It's how the r is changing as t is changing a little bit. Okay? Now, to make it a unit tangent vector, divide by its magnitude. So that was the next thing I did, was take this vector and divide by its magnitude. That's going to be the square root of 1 squared plus 2t squared, which is 4t squared. Right? Now, that's in terms of t. So let's put that together. The unit tangent vector, and this is a unit vector, so I'll put the caret over it. Okay? Unit tangent vector as a function of time is going to be I plus 2tj over the square root of 1 plus 4t squared. Okay? But they asked for it, I'm so sorry. They asked for it specifically when t is equal to 1. It doesn't have to be 1 second, it's just t is equal to 1. This t unit tangent vector at t equal 1 would then be I, that doesn't change any, plus 2j divided by the square root of what? 1 plus 4. So that would be I over root 5 plus 2 over root 5j. Okay? Now, if you don't like root 5's in the denominator, you can put it as root 5 over 5i plus 2 root 5 over 5j. Okay, however. Now, one thing to check, to me, make myself feel really warm and fuzzy about it, is to make sure that it's a unit vector. Well, 1 over root 5 squared would be 1/5, plus 2 over root 5 squared would be 4/5. 1/5 is 4/5 is 1, square root of 1. Yes, that is a unit vector, and it's in the direction of that tangent vector, I plus 2tj, at t is equal to 1. All right, does that make sense? And actually, how they wrote it, which is perfectly fine too, is 1 over root 5 times I plus 2j. Okay, there's another way to write it. There are so many different ways you can write these solutions that are absolutely correct. I mean, the first one, if I made that up square root of 5, that would have been fine, that would have been fine, this would have been fine. However, if you are doing WebAssign, they only look for one correct answer, even though there's a multitude of ways you can express an answer. Okay? So I don't know how they deal with parametric equations, because there's an infinite number of parametric equations to any equation. So you would have to know exactly which one they're looking for. Okay. Now, just as an illustration of this, oh, maybe they'll show that, so I won't have to go into it. Let me see if they show that illustration. Let me clear my Scratch and see how they do it. Well, first, to take a derivative of that r vector, and they got exactly like we did, I plus 2tj. The unit tangent vector, they just skipped right to that, is r prime over magnitude of r prime. Magnitude of r prime would be 1 plus 4t squared, just like we got. And r prime, of course, is I plus 2tj. When you plug in t is equal to 1, you get 1 over root 5 times I plus 2j. Okay? Now, double the class size. That's good to see. Even though it is just a zero. No, I'm sorry. Okay. All right, there we go. We're just finishing example 1 on page 845. This is the first page in section 12.4. And my throat is heading out to lunch on me. My nose is running. I just had a couple of sneezing fits, so I don't know what's going on there. I did have a student this morning that was complaining the room was really way too cold. She had to go get a jacket out of her car, and it is cooler than I think it should be. I have they don't give us any control of the temperature, but it says it's 72 in here, which is interesting. I would have thought it feels much cooler than that. I don't know if it. Okay, so they draw the picture of this. Now, here is the vector RT is equal to T plus T squared J. If you look at that, if you say X is equal to T, and Y then would be X squared, right? T squared. Okay? So that's a parabola. Y is equal to X squared. Okay? And that's exactly how it would look. Now, given the orientation of this, when t is 0, this would be at 0, 0. Okay? At t is 1, you'd be moved over here to t plus j, right there. So obviously, and if you had negative t's, they would be coming here. That would be a minus t for the x, and positive t's for the y, of course, but you'd be on this side. So obviously your curve, the transit over the curve is in that direction. Direction of the unit tangent vector depends on the orientation of the curve. And this one would be in that direction. But of course, this shows it to you. I plus 2j, that would be the tangent vector in general. 1i, 2j, so it has a slope of 2, this line here. And might be a little hard to see here. It's going up 1 or going over about 1/2. So that looks. So they do give another. Sorry. Indication at the bottom. I don't think they're going to do. Let me see if they do this on the slide. No, they don't. Sorry, I wish I could quit doing that, but I can't. The R of t is equal to negative t minus 2I plus t minus 2 squared j. Okay? Now, that curve, I'm not sure they're claiming it. Okay. It has exactly the same shape of this curve. Okay. However, it's at a different orientation. Okay. At least I want to say that. It may be at the same place even. But if you had done the R prime of this one, what is your R prime there? Your R prime. Okay, be a minus I. Do you see why it's a minus? Derivative of minus t would be minus 1. You see? That minus outside there. When you distribute the n, it would be minus t plus 2. Derivative of 2 is 0, but that would be a minus there. And then, what would be your second part? Plus 2tj, which is exactly like your R prime was before, except that was a plus here. So now it's a minus 1 over 2t, and obviously that is going in exactly the opposite direction of this one. Okay, going just like that at t is equal to 1. So I don't know if it's necessary to go any further, but say that they say the unit vector would still represent the unit vector at 0.11, but it would point in the opposite direction. Verify it. I think we just did. Okay, it's pretty obvious. There's that. And here's Justin. Okay. 3 here and missing 3. Okay. All right, this is the paragraph or a couple sentences at the top of page 846. We're in section 12.4. Yeah. Oh, good deal. Thank you. I think that's the first paper for this class. Way to go. Keep those coming, folks. tangent line to a curve at a point is the line that passes through that point and is parallel to the unit tangent vector. Okay? The tangent line to a curve at a point is the line that passes through that point and is parallel to the unit tangent vector. Okay. In example 2, the unit tangent vector is used to find the tangent line at a point on a helix. That's sort of a spiral going up or whichever direction it's going. So this is obviously a space curve, not a plane curve like the last one was. So let's see what that does. Here's example 2. Find the unit tangent vector, that's what capital T of t is, and then find a set of parametric equations for the tangent line to the helix given by this vector here. Okay? So, what is going to be your first step? Anybody? Yeah, take a derivative, r prime of t. And what would that be? Anybody, help me out. Negative 2 times the sine ti, I can't write. Next, plus 2 cosine t j plus k. All right. Yuck. Sorry about all this noise. Okay. What's the next thing we need to do if we're finding the unit tangent vector at a point? Okay, now we do the magnitude of that r prime of t. And we're going to start with it of t, and then we'll come and plug in the value. And what will that be? Okay. The square of the first is 4 sine squared t. Is that what you were saying? Okay. Plus 4 cosine squared t plus 1. Perfect. Okay. Now, is there any way you can simplify that? Any ideas? Let's group those two terms together and see what we get. The square root of 4 sine squared t plus 4 cosine squared t plus 1. What might you do with that? Anybody? Yes, factor out of 4. The square root of 4 times, and what's left inside? Sine squared t plus cosine squared t plus 1 outside. Okay? Anything else, folks? Yes! Sine squared t plus cosine squared t. Pythagorean identity, that's 1. So this will be the square root of 5. They seem to like square root of 5, don't they? So there is your magnitude of that vector at any point, not just at point that point at any point. The magnitude is that. So the unit tangent vector, and that is a unit vector, so I'll put a little cap on it, at some value t, any value t, would be let's do it like they did before. Take the 1 over root 5 outside, and then just write minus 2 sine t I plus 2 cosine t j plus k. Okay. All right. Now let's plug in, whoa. They say at the point square root of 2, square root of 2, pi fourths. Sort of a strange way to give it. Usually you would think they give you the value t. But they give you this point. Well, what's something you can pick off this point pretty straightforwardly? This is your vector, and this is the point that you're dealing with. What can you tell me, just looking at that, a value? Now this is a point, but you could be referring to a vector that's pointing toward that point. Okay? I hope that's not giving away too much. So just looking at this, if this point is on that curve, and they indicate that it is, then this is the x value, the y value, the z value. In other words, the component for I, component for j, component for k. Well, what is the component for k? T. So t is equal to pi fourths. Now, is that consistent? If you put t is equal to pi fourths in here, what's cosine of pi fourths? Anybody? Cosine of pi fourths. Something like that. Square root of 2 over 2. Multiply that by 2, and you have just the square root of 2. Right? What's the sign of pi fourths? Square root of 2 over 2. And multiply that by 2, you lose the 2 in the denominator, it's root 2. Yes, we know looking at this exactly what value t is. T is equal to pi fourths. Okay, so now that we know that, we can give the unit tangent vector at that value t. Okay? All right. And that's exactly how they did it. I wondered why they... So the unit tangent vector at t is equal to pi fourths will be 1 over root 5 times... Now you tell me what the vector is there. Second? Okay. It would be negative root 2, right? If t is equal to pi fourths, then sine of pi fourths is root 2 over 2, and that would be negative 2 times root 2 over 2, which would be negative. Okay. I, that means yes in Navy speak, okay. Next. Next. Plus root 2 j plus k. No variable dependence there, it's just k. Okay. Now, you might be concerned, is this truly a unit vector? I indicated it was. Let's see. Root 2 over root 5 squared would be 2/5, right? Yep. Root 2 over root 5 squared would be 2/5. 2 over root 5 would be 2/5. That would be 4/5 plus 1 over root 5 would be 1/5. 5/5. Yeah. That's 2 plus 2. 2/5 plus 2/5 plus 1/5 is 5/5. Okay, so it is a tangent vector. So there's the first part. Find T of T. We did. Oh, we already did the first part. And then find the set of parametric equations for the tangent line to the helix given as that. Okay, so we find T of T and then find the set of parametric equations for the unit, for the tangent line to the helix given by this formula at the point there. Okay, so there's the unit tangent vector that basically gives you the direction. Okay, and I'm going to change something ever so slightly, even though the book did it this way earlier. I'm going to change this as minus root 2 over root 5 I plus root 2 over root 2 over root 5 J. That's so ugly. Goodness gracious. Plus 1 over root 2, root 5. I keep doing that. K. Okay. See if I can clean that up a little bit. Okay, that's better. Whew. Oh, I think I forgot to tell y'all at first. I taught 3 classes today, and I can't remember what I told which one. If any of you were wondering why I'm dressed like this today, you probably weren't. But I've got a funeral to go to this afternoon. So I normally have office hours from 2 to 6 on Mondays. Not today. As soon as we finish this class, I've got to get everything sort of wrapped up here and packed up and head out. And I'll be going to the funeral. I talked with my boss. I thought I might go back to the Birmingham campus after that. He said, no, just go home and work, and that will save me 30 hours of driving there, 30 minutes of driving there and 30 minutes of driving back. So it saves me an hour. So I will be going first to the funeral, then I'll go home. So if you need to contact me, you can email me, and you can catch me that way. But most of the time, not many of you come by on a Monday afternoon anyway. But I just wanted to let you know if you were looking for me, I'm not going to be there. Okay, so there's the unit tangent vector written in that form. Okay, there's a reason for that. All right. What we need is a set of parametric equations for the tangent line to the vector there at the point root 2 pi fourths. Okay? Now, we've done the first part, and they did it just like I did. I was suspecting it would 1 over root 5, 1 over root 5 times, open parentheses, root 2 I plus root 2j plus k. Exactly right. Now, they use just these numbers, root 2, 1. Okay? They said direction numbers, and the point is root 2, 4, pi fourths. Okay? you can obtain the parametric equations given the parameter s, okay? Not using t, they've already used t up in the original problem. You don't want to confuse those. Make up a new parameter, and they chose s, which is perfectly fine. Then your, goodness gracious, where did all that come from? Well, this is driving me nuts. Okay, there we go. We got that back again. What your parametric equations are, if you remember, for x is equal to, and let's see, this is back, I think, in 12.1. So I just wanted to point you back here so you'd know where we're talking about. Well, I thought it was 12.1. Maybe 12.2. No, actually it's back in 11. I'm sorry, that's what. Okay. Yes, lines and planes in space. Okay. Theorem 11.11, this is on page 787. A line L parallel to the vector, and here we have our vector, passing through a point, there we have our point, is represented by the parametric equations. X is equal to x1 of the point plus this coefficient here times s in this case. Okay? So that's where you go to do this. Now, I was going to use these numbers, but yeah, the directions, it is a lot simpler just to use the root 2. So that would be root 2 plus, or minus, because that is a minus there. Okay. Root 2s, y is equal to just done something stupid there, I think. No, that's right. Root 2 plus root 2s, and z is equal to pi fourths plus s. Okay? Yeah. Now, yeah, there you have the parametric equations. Root 2 minus root 2s, root 2 plus, what x is that? Y is root 2 plus root 2s, and z is pi fourths plus s. Okay, that's your tangent line. Now, as they say here, in example 2, there are infinitely many vectors that are orthogonal to the tangent vector. One of those is the vector t prime of t. Okay? Now, why they're using that one is not clear. Nothing we did was indicating this, but they're using example 2. I don't know if you can see. Goodness, my eyes hurt. A vector that's perpendicular to a unit tangent vector. Okay? It may not be exactly obvious to you, but one of those vectors is the vector t prime of t. Now, here my nomenclature gets into a little bit of a problem. Excuse me. T is a unit vector, okay? So I put the caret over it. The first derivative of t, though, is not necessarily a unit vector. Okay? So therefore, if I put the prime by it, if I put the caret over it, that would be indicating t is a unit vector, but not t prime. So rather than do that, I'm going to go back to putting an arrow over the t, not the caret or the housetop or whatever you call it. Okay? But they say that their claim is one of those is the vector t of t. Okay. If you go back to property 7 of theorem 12.2, that was back, I believe, in section 12.1. See if I can find it. Theorem 12.2. Well, I don't see it in 12.1. Theorem 12.2 on page 830, right at the bottom of the page. Okay? Property 7, if R of t dot R of t is C, then R of t dot R prime of t has to be 0. So if a dot product of a vector with itself is a constant, then the vector times the first derivative of that vector has to be perpendicular, orthogonal. Okay? Now, all right. Now, I really don't see how it can help but be, okay? A dot product of a vector times itself, dotted with itself, is always going to be a scalar, okay? I guess I was going to say the only exception would be if the 0 vector, which would be a scalar, but it wouldn't be worth anything, but then the vector itself would have to be a 0 vector. So for any non-zero vector, dotted with itself is going to be a scalar quantity. Therefore, this is saying any vector times the derivative of itself has to be the 0, the number 0. They have to be orthogonal to each other. Okay. So we're just going to sort of let that slide by, and we know that unit tangent vector times the unit tangent vector is, the magnitude is 1, because those are both unit vectors, okay? And so therefore t dotted with t prime has got to be 0, okay? Now, I think that's going into stuff after this problem. Let's clear this and finish this problem. And I think maybe they'll pick up that on the other slide. So let me see. Derivative of that is r prime of t, just like y'all said, minus 2 sine t plus 2 cosine t plus k, which implies the magnitude of that, r prime, is going to be the square root of 4 sine squared plus 4 cosine squared plus 1. And that's going to be root 5, because if you group these two together, factor out the 4, then you have sine squared plus cosine squared, which is 1. 4 times 1 is 4, plus 1 is 5, so it's square root of 5. Okay. Therefore, the unit tangent vector is that, which is 1/5 times 1 over root 5 times minus sine ti plus 2 cosine tj plus k. Okay. So sorry. Root 5, 1 over root 5 is over every one of those terms. Okay. Root 5 is under each of those terms, I guess. Now at that point, the unit tangent vector is this. And plug that in. And of course, your root 2 over 2, when you multiply by 2, minus 2, gives you minus root 2 plus root 2 plus 1, all over root 5. So factor out the root 5. And it says here, using the direction numbers, A is equal to negative root 2, B is equal to positive root 2, and C is equal to 1. They're not the coefficients of the unit tangent vector. They don't have to be. They're the coefficients of the tangent vector. That's all you need. And that you have this as your point, x1, y1, z1. Then you can obtain the parametric equations by x is equal to x minus this times t. I'm sorry, that's s. We've already used t. Sorry. Y is equal to root 2 plus root 2s. Or discretion, they say A, B, and C, and then they're later going to put it in. Oh, they're just doing x1. They're showing you the form that I was, yeah, there it is, root 2 minus root 2s. X is y1 plus bs, which is root 2 plus root 2s, and then y, or z is equal to c1, which is 1, not pi fourths, plus 1s, or plus s. Pi fourth plus s. Those were the things we did. Oh, and here's a picture of it. Thank you for drawing it. I didn't want to. Here is the helix going up around the z-axis, okay? And that's the curve that it's following. It's starting here, going this way, this way, this way, this way, all the way up. So at this point, t equals pi fourths, it's down here. This will be coming directly out of here. If you drop this line down here, it will be exactly bisecting that big angle there. 90-degree angle there. The tangent line to the curve is determined by the unit tangent vector at the point. So there's the tangent vector, divided by its magnitude to get the unit tangent vector, and the tangent line would be the parametric equation at that point with that direction, okay, which we just did. Now, okay, here's what I was trying to talk about before. I thought this was part of example 2. It's not. In example 2, there are infinitely many vectors that are orthogonal to the tangent vector, capital T. You can have here, 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 anything perpendicular. Okay, orthogonal to that tangent vector t. One of those is the vector t prime, and that comes from this. If the dot product in that property that we talked about before, they don't list a number here, theorem 12.2, property 7, that if a vector dotted with itself is a scalar, any scalar, C, well, this is a unit tangent vector dotted with a unit tangent vector. Any two vectors dotted with themselves, or any two vectors dotted, it's going to be a constant, including itself. Okay? And we also know that that is the magnitude of the magnitude of this vector squared. The magnitude is 1, and 1 squared is 1. So that's obviously a constant. Then that property, that t of t and t prime of t are orthogonal to each other, if that's a constant, obviously it has to be. So by normalizing that vector, t prime, which is perpendicular to the unit tangent vector, you obtain a very special vector called the principal unit normal vector. Okay? Now, most texts I've taught from just call it the unit normal vector. Okay? They don't usually say principal, but principal means it goes to the inside of the curve. The other one goes on the outside of the curve. So this is the principal one. It's indicated in this definition, and here we have it. Oh my. Okay. Let C be a smooth curve represented by R on an open interval of I. Okay? I is the interval over which T is defined, little t. Okay? If T prime of t is not equal to 0, okay? In other words, the unit tangent vector, yeah, this is almost a ridiculous statement. Oh, no, I'm sorry. If the derivative of the unit tangent vector is not equal to 0, sorry, it wasn't unit tangent vector. The derivative of the unit tangent vector is not equal to 0, then the principal unit normal vector is defined as this, t prime over magnitude of t prime. Now, hopefully, you've noticed a similarity here. The unit tangent vector, okay, is equal to your r prime over magnitude of r prime. Okay, ooh. My pen's dragging. Okay, ooh, that didn't do well either. No. It was better off last time. Okay. I swear this is dragging all over the place now. Okay. So there's a unit tangent vector, r prime of t divided by the magnitude of that. Then take the derivative of this, and that t prime of t divided by its derivative of magnitude, that gives you unit normal vector, the principal unit normal vector. Okay? And by the way, what makes it principal is that it always points to the inside of the curve. Inside of the curve. Okay. So here's example 3. Boy, they're showing all these in here. That's good. Find n of t and n of 1 for the curve represented by this. New curve here, so where would we begin? If you want a principal unit normal vector, what would we have to do first? What's that? Take a derivative, is that what you said? Yes, okay. R prime of t is equal to what? Three I plus 4, what? 4 tj, perfect, okay? What do we do with that? Take its magnitude. The magnitude then of r prime of t is equal to what? Help me. 9 plus 16t. Okay. Now, what do those give us? That gives you the unit tangent vector. Okay? And what would that be? Unit tangent vector is this over that, right? Okay, so that would be this over that, okay? 3 over the square root of 9 plus 16t plus 4t oh, I left off the I. Okay. 4t over the square root of 9 plus 16 J. Goodness, these little lines keep showing up. Okay. Trying to get my pen back. There it is. Okay. There's the unit tangent vector. Whew. Now, unfortunately, what do we got to do next? Take derivative of that one, and that's really a pain in the neck. Okay? And let me take out those parentheses. I'm not sure why I put them in there. I think 4t looks better just by itself. Okay. That's not a plus sign, that's a t. Okay. So the derivative of that, now here's where I get into a little bit of a quandary. Okay. Okay. We may be all right on this. Okay. Boy, what a pain. All right. All right, let's do it. What rule are you going to have to use to take that derivative of the first term, of the I component? Anybody? If you don't mind, I would just about as soon use the product rule and write this as 3 times 9 plus 16t to the 1/2 power, or minus 1/2 power, I, plus now this next one, I'm afraid it's not going to make much difference, but I think I still prefer the product rule. 4t times 9 plus 16t to the minus 1/2 power. You could do the quotient rule, and I just don't care for the quotient rule that much. I'm going to try it this way, see if it'll be a little bit better. There is a reason to use the product rule here. What would that be? I mean, the power rule. I said product rule, the power rule. What would that be? Pretty straightforward. Take the derivative of that. Anybody? Okay. Now, I've messed up a little bit here. I changed my mind. That's your t of t, not t prime. It's just rewritten that one. Okay. Now we do t prime. Oh. Now, wait. Still got it backwards. Not backwards, but just a little bit wrong. Okay. Now, that's a unit vector. This one is not necessarily a unit vector, and that's why I put it back with the vector notation on it, just like this. Okay? T would have been a unit vector, and I'm taking the derivative of the unit vector, but rather than mixing it up and making you think this t prime is going to be a unit vector, I went back to calling that just a Now, take the derivative of that first term. Not that hard. What is it? Power rule, right? With the chain rule. What would that be? Help me out. Okay. Would be your exponent times your coefficient times this, drop one power, times the derivative of this, right? Chain rule. So the power rule tells you it's minus 3/2, that's the coefficient, the exponent times the coefficient, times the 9 plus 16t, and then you drop that by 1, which would be a minus 3/2 power, right? Then you do the derivative of the inside, the chain rule, and that would be a 16. Okay? What? I'm sorry, say that one more time. I hear you're saying something, I just can't make out what you're saying. Okay, you're right. Sorry about that. It's a t squared. You're right in both places. Okay. I thought something didn't look right. Okay. So we have a little more chain rule to do here. Okay. So we got it so far, but now we have the derivative of the inside, which is 32t. So that's going to multiply by 32t and multiply that by negative 3/2. That would be a minus, well, 2 will go into 32, 16, minus 3 times 16 would be minus 48. Okay? If I'm doing my math right, okay, that would be a minus, yuck. This thing is not running well. Okay. Minus 48t over, I'm going to put it back downstairs now, 9 plus 16t squared to the 3/2 power. It was a minus 3/2 up there. Okay, that's the I component. Now the J component is even worse. Okay, product rule. Okay, let me clean up this just so you can read it better. Okay, that's a 9. Okay. All right. How do you like to do the product rule? What is that for you? Now, if you prefer quotient rule, go on back to the top one and do the quotient rule, but I find the product rule is just a little easier to do or easier to keep up with, but in this case, it's not particularly easy, period. But what do you do here? How does product rule go? The first was a power rule with the chain rule. This will be a product rule, which incorporates the chain rule. Okay? Twice it will. Okay? So what would that be? How do you do the product rule?
If you multiply 4t to the 9 plus 16 first?
No. Okay. These are two different functions here. And this is to the minus 1/2 power. So this would really be, this is exactly that. And you wouldn't multiply those two things together. Right? Okay. So what you do, depends on how you like to do it. First time derivative of the second plus the second time derivative of the first. Or vice versa. You can do second time derivative of the first plus first time derivative of the second. Which way you want to do it? Or the way you're most familiar.
First time.
First under root of the second. Okay, we'll do that. Now I'm going to run out of room. I know I am. So that's going to be 4t times the root of the second, which would be what? Very similar to what we had before. Yeah, it's going to be a minus 1/2 times 9 plus 16t squared. Oh, goodness. I hate this. I'm trying to cram my writing together and the pen gets off a little bit. T squared to the minus 3/2 times your 32t, which that's going to be 16t. Okay? All right, that's the first part. Okay? The second part is going to be a plus. It's the second times the root of the first. 4 times 9 plus 16t squared to the minus 1/2. Okay? And that's all times the j vector. All right. Now this is a real pain in the neck. Okay? But it's doable. Here I went to do it again. Again, I'm going to put this as a vector rather than a unit vector. T prime of t is then going to be all right. I already got the first term done okay. Now, understand that I didn't do the chain rule up here. I did it down here. I did it in two parts. So that's minus 48t over 9 plus 16t squared to the 3/2 power, and that's all times I. Now let's see if we can congregate our j term the same way too. I'm going to lead off with the first one. This is going to be a 4 over the square root of 9 plus 16t squared. There, that's to the minus 1/2 minus 4t. Let's see. Let me combine those together. This really gets awkward. Understatement. 4t times 16t would be 64t squared over 9 plus 16t squared to the 3/2 power. Okay. And that's your j. Wow. Okay. And then guess what we got to do? We got to take the magnitude of that. And I really don't want to. Okay. Here's what I'm going to suggest. In fact, I'm going to look at this and make sure it's legal. Nope. They haul the T around the whole way. Yuck. All right. And then they do a really strange thing of rearranging these, which I guess is okay. Let's make sure we're on the right track here. Our t of t up here is 3i plus 4tj over the square root of that. So we got that right. Okay? And then we took the first derivative of it, and we got 4t, and they do it in a strange manner. Okay. They don't show you how they did the derivative, but they do it. And then they do first the positive part, which is 4j over the square root of 9 plus that. Okay, agreed. Minus, and then they pull out a 16t, which leaves a 3t out there, over that to the 3/2 power. That's the I component, yeah, minus 3 times, yeah. And then the second part of this one was a plus 4. Did I leave off my t? I think I left off my t. Yes, I did. No? No, that was the other part. Sorry. There's my 4t. I've got it now. 4t times 16t. Yeah, I got it. Yeah, over that. So those parts are okay. Now, what they did next here, man, I'm having trouble following how they went to the next step here. We are in complete agreement down to this point, but then their next statement okay, if you combine the okay, 16t times the okay, that's my 48t there, minus 48t. I've got that part. They factor out a 12 and have a minus 4t times that, 12 over this thing. So I agree with that, 4t. And then the second part, okay. I am really having trouble figuring out how they got that second term there. I'm sure it's right, but it's surely not obvious. Okay. The I part is correct. I agree with that. They wrote this as a minus. I'll put it the way they did. They did it as a 12 over the square root of, let's just leave that in 3/2. They mix up their symbology. That also makes it hard to follow. Okay. 12 over 9 plus 16t squared to the 3/2 power. And what does that leave you with? A minus 4ti. because factor out of 12 you get minus 4ti. Okay. Now, what is not so obvious is what they do next over here. And I'll tell you, here's what I think they've done. They write this as multiply this numerator by 9 plus 16t squared and divide it by 9 plus 16t squared. Okay? Now, in the numerator, you get a 36 plus 64t squared, and this becomes your same denominator as you had before. Okay? Yuck. Okay, I'm going to separate these. Plus, okay, what I just said, 36 plus 64 t squared over 9 plus 16 t squared to the 3/2. Okay, minus 64t squared. I see how it's happened now. 64t squared over 9 plus 16t squared to the 3/2. And that's times j. Okay. These two disappear. One's plus and one minus. And that just leaves them with 36, which if you factor the 12 out, that leaves a, this term here is 12 over square root of, 9 plus 16t squared to the 3/2, and then what you have left is 3j. So sure enough, that is right. What they did is correct. Okay? Now, boy, what a pain in the neck problem this is. Okay. What you've got to do next is take the magnitude of that. So I'm going to clear out a lot of stuff here so we can go back and take the magnitude. I want to leave the stuff I need to leave. So I need to leave that numerator up there. Actually, I don't need that anymore. I don't think I need the t either, but I'll leave it just in case. So, to keep from, so I'm going to go back and just write in what they got as their answer, because we got it too. I just did it, but I don't have room to keep it. So here's what the t prime is. T prime of t is equal to, okay, 12 over 9 plus 16t squared to the 3/2 power times 4ti plus 3j. All right. Now, I'll take out the rest of this because I just don't have room to keep it any longer. This is how we got it, but I'm factoring, getting rid of all this so I can write some more. I hate these that just go on for ever and ever and ever on this small screen. If I was using the board, I'd take up both boards with it, and it would all be there in front of you, but then it wouldn't be recorded. So in order to keep the recording, I have to do a lot of erasing. Sorry about this. This has really turned into a pain of a problem. So what we have to do now is do the magnitude of this, okay? Which is, now this is all an expression right here, okay? And what the magnitude of the t prime of t is the square root of, and you would do this thing squared plus that thing squared. Well, obviously, you're going to be squaring this thing both times, so let's go on and pull that out of the square root, okay? You're going to square it and then take a square root of it. So basically, that leaves you with just what you had to begin with, okay? Which is 12 over 9 plus 16t squared to the 3/2 power. Because you squared it and then took a square root of it, okay? Now, we're going to come back to that in a minute, okay? And then it's going to be the square root of this thing, 16t squared plus 9. Well, look at that. This is a factor up here as well as down there. So if you take this out, basically you lose the 1/2 here, and you just have, let's see how to express that. This is this times this times this, and that is just that. So you have this to the 0 to the first power then. You know, subtract the 1/2 from the 3/2. So that's what you wind up with, and that's how they get 12 over 9 plus 16t squared, okay? That is your t prime, the magnitude of t prime. So what is your unit normal vector? The unit normal vector is a function of time. Real pain is the unit tangent vector, which would be 12 over 9 plus 16t squared to the 3/2, okay, times 4ti plus 3j. Then divide this by 12 over 9 plus 16t squared. Well, the 12s are going to go out, and this will go into that 1/2 power, okay? So what we wind up with is, how do they write it? Yep, they write it just like that. 1 over 9 plus 16t squared to the 1/2 power times this vector 4ti plus 3j. Okay. Except I've dropped a minus sign somewhere. Yeah. Yeah, it's minus 4t, and I can't see. I think it was on an earlier term, and I completely, yeah. Because here, this minus was in front of that, and I wrote it up without it. So that's a minus, that's a minus, and that's a minus. Sorry about that. When I did the translation, I'll drop the minus sign, I think. Okay. All right. So that's your unit normal vector for any t. Whew. We finally get back and do it for 1. N unit normal vector. Oh, and this is a unit vector. So let me go back and put my notation in. It is a unit vector because you're divided by its magnitude. Okay, so that at 1 is just plug in a 1. So it would be 1 over 9 plus 16 to the 1/2 power. Well, that's going to be 25, so that's 1 over 5 times a minus 4i plus 3j, which is going to be, this is 5 down here, minus 4/5 I plus 3/5 j. All right. Now, let's take a look at that for a moment here. Is that truly a unit vector? Okay. 4/5 squared is 16/25 plus 9/25. That's true enough. It's 5/25. Yes, that is a unit vector. Okay. And they wrote 1/5 in front and then minus 4i plus 3j. Wow. What a pain in the neck problem that was. Okay. It did simplify greatly, but it was really a tough thing to see. Now, the principal unit normal vector can be difficult to evaluate algebraically, as we just saw, okay? For plane curves, you can simplify the algebra by finding the unit tangent vector, okay, and observing that n of t must be either, it has to be perpendicular to that, okay? So if, I think they're going to have this on the slide. Well, before we go any further, let's clear what I did, and let's see how they did the problem. Okay, by differentiating, we have r prime is 3i plus 4tj, just like we did, which implies that the magnitude of that is the square root of 9 plus 16t squared. Yes, there was your t squared. Okay, so the unit tangent vector is the r prime divided by the magnitude of r prime, which is 1 over the square root of 9/16 times this, 3 plus 3i plus 4tj. Okay? That's your unit tangent vector. We got that. Okay? Now, to differentiate that, what a pain in the neck that was. They skipped tons of steps to get there. Okay? And I went back and reconstructed them all, and that is correct. But boy, what a pain it is. Okay? Now, and they wrote it so strangely with a j part here and an I and a j part over there. But it's correct. Okay, we verified that. Now that's the unit tangent vector, the first derivative of that, which is not a unit vector. The unit tangent vector is a unit vector, but its first derivative is not. So we are going to need to, okay, now, how did they get from there to here? Okay, let's do the i's first. Okay, and I did this one for you, so I'm not going to carry it out in gory detail. This is minus 48 ti over this thing plus 64 t squared j over that thing. No, and that's a minus 2, because that would be a minus, and that's where we drop the sign, I think. Minus 64j. And then this one here is just a plus 4 over this thing. Now, to get from that to this, we multiplied this by 9 plus 16t squared, and that would be this thing to the 2/2 power, so that gives us this. So this is 9 plus 16t squared times 4. 9 times 4 is 36 plus 64t squared. That, okay? Well, the plus 64t squared and the minus 64t squared, they go out. They add to 0. And that left us a 36j over this thing. So there's your factor out of 12, and there's your 3j over that thing. And then this gave you a 48, factor out of 12 out of that, 48t, factor out with a minus, and that gave you a minus 48t, factor out of 12, and that left you with minus 4t. So there was your minus from right there. and that's the I component. Now, the magnitude of this would then be the square root of this thing squared, which basically pulls that thing out. Now, they left it in here. Don't know why. No real reason why that I can see. I would have, like I did, I carried all this thing to the outside, and then what you had here was 9 plus 16 t squared. And you square that, okay? Well, I guess I see why they did it. Because this square root will go into that then. This is one of these and 3 of these, so that goes in squared, so it's 1 over this squared, so that pulls it on the outside, making it just 12 over this thing, okay? 9 plus 16 t squared. So that's the magnitude of that. So we're going to take this and divide it by that. Well, obviously the 12s go out, and one of these goes out, leaving you just with 1/2 down here, times that. And that's exactly what they wind up with here. 1 over the square root of that times this thing here, minus 4ti plus 3j. Okay. There's your n of t. And then to do the t equal 1, 9 plus 16 is 25, square root of 25 is 5, times this thing. So they just left it like that and drew it in over there. Now, here's the thing to note. Your t everywhere is perpendicular to the n. T of 1, n of 1, t of t, n of t. They've got to be perpendicular to each other. We already established that. And since this is such a pain in the neck to calculate, if you can get the t of t, or unit tangent vector as a function of t, or as a function of anything, then what they suggest on the top of the next page is this. The principal unit vector can be difficult, blah, blah, blah. I just said that. So if you have this t of t, which is some x of ti plus y of tj, and you know that that dotted with n of t has to be 0, then either multiply this by y of t and this by minus x of t, which gives you that, or multiply this by minus y of t plus and multiply that by x of t, and that gives you that. Okay? So one of those has got to be true. Observing that either the n of t must be this, so when you dot those two, this gives you a plus xy minus xy, which is 0. This gives you a minus xy plus xy, that's 0. One of those has to be true, and you just have to figure out which one is your principal. Okay? So how do we do that? Because, okay, now, x of t squared plus y of t squared has to be 1 because it's a unit vector, right? Are we out of time? Oh, we're well out of time, aren't we? Okay, sorry. But, as we want, it follows that n1 of t are both unit normal vectors. The principal unit normal vector is the one that points to the concave side, the inside of the curve. So it's whichever one points inside the curve. That's what you always go by. And I think we'll hold that for now. We'll start next time. Goodness, that was a pain in the neck. We'll do that. We'll start with this figure here next time. Now that's okay. Believe it or not, well, no, we didn't. We still got a ways to do in 12.4. Homework exercises here, any of the odds 3 through 7, they're all at Calc Chat, 5's at Calc View. Any of the odds 9 through 13, they're all at Calc Chat, 9's at Calc View. Any of the odds 15 to 19, they're all at Calc Chat. 15's at Calc View. Okay. I think you can do 21 or 23. They're both at Calc Chat. We'll hold off there and do the next time. All right. Sorry about that. Okay, let's end this now.